In the previous lecture, we have remarked that a matrix is a good model for a bunch of real numbers. To each of them, when to each of them is assigned a particular place of positive integral coordinates in a two-dimensional plane. So we'll consider now the probably the most notable example of such a situation, and the application of matrices is going to be dealing with the field of system of linear equations. In order to define what a system of linear equations is, we need first to define what an individual linear equation is. So here's the definition. A linear equation is the following object. It is a string of letters a1 x1 plus a2 x2 plus so on ak x k minus b, and then an equality, a symbol of equal, and the number 0 on the right hand side of the equality. So this object is an equation. Now let me say a few words about what the a's are and the xi's are, and also the b's. So a's and b are unspecified but fixed real numbers. They are called coefficients and constant term respectively. So b is called the constant term, and the ai's are called coefficients. So coefficients usually is something that is related to something else by a multiplication, and since these ai's are fixed real numbers, we'll see in a moment that this is indeed the real number multiplication. So what are the xi's then? Xi's are unknown real numbers. So they are also real numbers, therefore a1 x1 is meant to be a1 times x1. And the plus is as a real number, a2 x2 means a2 times x2. To notice the difference between unknown and unspecified. The difference is that unspecified but fixed means that I picked these numbers, but I don't know what they are because the statement I'm doing holds for any number. Okay, but I fixed them. Whereas xi's, they are not fixed. They are real numbers, but they are not fixed. They are allowed to vary. So the meaning of this string of characters is exactly for ai's constant and xi's varying. Let's see an example. An example is the following. We have this string of numbers and letters, and then equals to 0. Okay, so what is a1? a1 is 3 in this case, times x1. So we have the perfect analogy here. And then we have plus, and then x2. So x2 means that the coefficient of x2 is 1. So is the number 1. So in this case, a2 is 1. Then there is no x3. As you notice here in this notation, we have all the xi's between 1 and k. They are all present here. Now why here x3 is missing? x3 is missing because the coefficient of x3 is meant to be 0. So these ai's are real numbers, so they might be 0. In the case one of these is 0, of course the product of this 0 times any xi will be null. Okay, so here x3 is not appearing because it is understood that the coefficient of x3, a3, is 0. Therefore that make the summand vanish. Then we have the x4 term with the coefficient -2, so a4 is going to be -2, and then we have plus 2 equals to 0. So plus 2 is not a coefficient of any xi, therefore it is the constant term here, minus b. Therefore b is going to be -2. To each linear equation we can associate a subset of Rk. In which way? So we consider, say, C1, C2 up to Ck. So these Ci's are real numbers, such that if we replace the Xi's with Ci's and we expand this sum, okay, we will be getting an equality between two real numbers. So that means that plugging in the values for Xi's Ci, we will be getting a 0 here on the left hand side of the equation. Okay. So this k-tuple is then called a solution of the equation. Okay. So a solution of the equation is a k-tuple of real numbers such that when plugged in for the variables xi's and expanded in the expression here on the left side of the equation, I will be getting 0. So this is a subset of Rk, can be empty, so there can be also cases in which the equation has no solution, or can be, well, we will see later what kind of shape these set of solutions of a linear equation in Rk has. We pass now to the definition of system of linear equations. Definition: a system of linear equations is an ordered set of n linear equations in the same variables. So if you notice, here was the example of one linear equation. Here we have n of them, ordered. Notice the important remark. While before the coefficients ai's had just one index, and the index was matched with the index of the variable, here it is very convenient to introduce a second index, so we will have aij's instead of just ai's, where the first is matched with the equation to which it belongs to, and the second is matched with the variable. Therefore here the first coefficient or the first summand of the equation is going to be a1, 1, because it is a coefficient of the first equation, and it is the coefficient of x1. The second coefficient of the first equation will have indices 1, because it is again a coefficient of the first equation, and then comma 2, because it is the coefficient of x2, and so on. So we'll end up with a1k being the last coefficient of the last variable. Now the constant term, before it was just a b, because there was just one equation. Now the constant terms here are not necessarily the same throughout the equations. Therefore we have to introduce an index for the constant term as well, and an index is sufficient because this index is going to be matched with the equation to which it belongs to. So for the first equation there will be a b1. Now the second equation will start off with a a2, 1, because 2 means that the coefficient is of the second equation, and then 1 because of the first variable of the second equation, and so on. The last one being a2k minus b2, b2 because again is the constant term of the second equation. So on as we go along with the equations until the last one, which is the nth, and we will have an comma 1 x1 plus an comma 2 x2, and so on, the last one being an comma k xk minus bn. So as you notice here we have a bunch of coefficients depending on two indices. So it's absolutely natural to associate a matrix comprising all these coefficients, because we have real numbers, so these aij's are all real numbers, and they can be precisely placed in a plane in places with integral coordinates starting from 1 1 onwards. Okay, so in this case 1 1 will be going to 1k and in one direction, and then 1 1 will be going to n1 on the other direction. So this will be a matrix with n rows and k columns, the associated matrix to this system. This is going to be exactly called associated matrix of this system. What is the analog of a solution of a linear equation in the case of a system of linear equations? The analog is the following. The set of solutions of double star, which is this system of linear equations, is the subset of Rk of vectors C1 through Ck, satisfying all the n linear equations simultaneously. Therefore, if you want, is the intersection of all the solution, the set of solutions of each of these linear equations. So they have to, these k tuples of real numbers have to satisfy simultaneously all the n equations. Once again, the possible outcomes are: there is no solution at all, there is a unique solution, or there are infinitely many solutions. As you notice, there is no possibility of having a finite number of solutions except the unique solution. There cannot be 2 solutions, 3 solutions, or 4 solutions. This follows from the fact that we are looking at solutions in the field R. So these CIs, C1, C2 through Cn, through Ck, are real numbers. So we are looking at a set of solutions in R to the k. If we were to look at solutions in another Cartesian product of another field, for example a finite field, then in that case we could have finite solutions with a number of solutions different from 1. But we will not be treating these fields in this course. Notice that if there is no solution at all, we can still investigate inside Rk if there is some linear hyperspace, hyperplane, that somehow gives the approximation to all these n equations. Okay. So we are looking at n tuples, k tuples in Rk, which belong to a linear subspace, and somehow give the best approximations to solutions to all these n equations. Of course, there is not exact hyperplane passing for all the individual solutions of each of these equations, because we are assuming that there is no exact solution at all. But we can still try to wonder how to find the best fitting to all these individual solutions of every equation. And this technique, which is called linear regression, and is very interesting technique used in data analysis, but we will not be covering anything of this in this course. In the case there are infinitely many solutions, they all have the affinity which is equal to the continuous, but we can still tell apart 2 of them according to the so-called dimension. In the next lecture we will see that the set of solutions of a system of linear equations have a particular geometrical shape, and we can associate to this set always a dimension. Therefore, the solutions may have dimension 0, in which case we are in the case B, there is a unique solution, or dimension 1, and in that case there are infinitely many, or dimension 2 and there are still infinitely many, dimension 3 and so on, they're all infinitely many, but still the dimension is different from each other. There can be, of course, two set of solutions of the same dimension, for example 1, but they are different set of solutions as a subset of Rk. We will see these in the next lecture. The question now is, what does this have to do with matrices? So as I already anticipated before, we can associate to this system of linear equations a matrix called capital A, whose entries are aij's, exactly as written here inside this system of linear equations. I should just erase the other symbols that are not aij's, and I just write two parentheses, one on the left and one on the right, and I have my matrix A. Using the vector space structure that we introduced on matrices in the previous lectures, we can rewrite this system of linear equations in terms of column vectors. Here is the writing. So A times X minus B, so X and B in this case are underlined, notice that, equals to 0. So when I underline a character, I mean in this case that I give this character a structure of vector. Okay, so this is not going to be just a real number, but it's going to be, in this particular case, a column vector of the appropriate length in order to make this expression have a sense. So A is the matrix, capital A is the matrix I mentioned before, so whose coefficients are the aij's of the coefficients of the system. X is a symbolic column vector whose entries are the symbols x1, x2, so on to xk. B is a honest vector in Rn, whose coefficients are the numbers b1 through bn. And 0 is simply the column vector with n zeros, n number zeros, written in a column. Now we see that, okay, this equality is an equality between two column vectors of length n. So 0 on the right hand side, and on the left hand side there is this column vector expressed as a product of two matrices and then a difference between two vectors. If one expands A times X using the definition of product of matrices, we'll easily see that this is going to be a column vector of length n. The first coefficient of this column vector is going to be exactly what I circled here. The second coefficient of this column vector is going to be what I circled here in the second equation, and so on. And then we subtract the column vector of the entries of B that are these real numbers here. Okay, so it's obvious to see that this equality between these two column vectors is just a rewriting of this system of linear equations. Moreover, if we are just interested, as we usually are, to the solutions of a system of linear equations, which is an object completely different from the system of linear equation itself. So if you are just interested to know whether the system has solutions or not, and if it has solutions, find them, or see at least the dimension of them, or which shape this set of solution has, we can apply the vector space structure of the set of matrices and rewrite this equality as A times X equals to B. All I'm doing in here is just summing up both sides of the equation with a column vector, with the column vector B. So if I sum it up here and there, so 0 plus B is going to be B, because 0 is the additive identity element, and negative B plus B is going to be 0, the 0 column vector, once again because of vector space structure of the set of matrices. So this is a different writing, if you want, from the point of view of characters, than this system, than this equality and this system, but the set of solutions of this equality is precisely the same as this, and precisely the same as this set of linear equations. This is the key writing of a general system of linear equations that you will be using.